All right, let me first put the date of this recorded video. So this video is for the preparation of the material for the complex geometry informal seminar hosted on Enjoying Math YouTube channel. Over the past 3 weeks, we have held weekly informal seminars, but I personally found that the lecture style format should not be ideal because the majority of the participants are already the level of the PhD in mathematics, and I felt that the lecture was not really necessary, but it should just trigger the conversation and discussion for the expert. So as a result, this recorded video is my first attempt at a new format where I prepare notes and the explanation within this video in advance using these materials as a foundation for the seminar conversation, which might not be recorded, aiming for the further research like the projects, potential writing projects, I mean. So, and I appreciate understanding of the participants and also the potential participants, and we'd like to continue to refine the approach through the trial and error. Thanks for understanding. So we are talking about from last week the Chern connection, and truth be told, I didn't even define what this is yet. So I let me just give you the necessary like the setting. So basically the connection is defined over the vector bundle. So vector bundle, the standard notation is the map projection map pi from the vector bundle E to the smooth manifold M. And I will not define this word, so please just search from the Google if you do not have a necessary background of the term of the vector bundle. I mean the basic like the level. And when we deal with the such a like the vector bundle, then usually we treat it in terms of so-called the concept of the sections. So also a section is usually denoted as a element of the gamma M and E. I think this is also standard notation. So it is the like the basically the object defined as a pi composed by this S satisfies the identity over the smooth manifold. That's a concept of the section. So that if one just draw the manifold as a sort of the real line, then so for each point we have the fibers, and this over like the plane is regarded as just the E, and the section is sort of the concept of the graph. So that if you take the projection via the map pi, then we just recover the zero section. And many times we also talk about the local sections. So the concept of the local sections, we just look at the open set inside of the smooth manifold. So open set, then we just sort of the restrict. Or it's not coming from the restriction of the global section, but it's just defined locally. So this S of U is just the element inside of the gamma from U to E. So that we just treat U as a smooth manifold and just repeat the same definition, provided vector bundle from pi from E to M is already given. And most of the time, we look at the just a smooth sections for simplicity. Before we are talking about the complex manifold. So smooth section just means that, and let me borrow the notation from the textbook of the principle of the Griffiths, like principles of algebraic geometry from Griffith and Harris. So this is the standard notation. A star of M and E as a graded like the structure that we have a direct sum from k equals 1 to infinity of each like the k like the degree. So this just represent the following. So each element in this a to the k consists of the following form, so that it is denoted by, so this guy is just nothing but the element of the tensor product of omega k times. So this k represent the degree of a to the k tensor by x. So here this omega belongs to the holomorphic cotangent bundle. Let me use this notation. omega sub m, depending on the context. But because we don't talk about the complex manifold yet, so for the smooth manifold, it's just a cotangent bundle. I mean, just as a section, just a notation for the section, and this X is just a usual section of the given vector bundle, so that we just take the k times like the tensor product in the cotangent from the section of the cotangent like the bundle. That's smooth as a sections of the a to the k, and also we can talk about the smooth local sections as well in the same way. So that we just restrict the manifold from M to U and just repeat the same graded like a structure basically. And now we have a vector bundle E, so that we can also talk about the metric defined fiber wisely, and it varies fiber wisely indeed smoothly. So otherwise we should just talk about the context. So the metric H is defined over the overall vector bundle E, so that we also assume rank is given by some chosen fixed like a non-negative integer k, so that we require for the complex manifold M later on. So mostly we will just talk about the complex manifold, so that this would be written in local coordinate as a h sub ij bar, and we require this to be Hermitian, and this should be positive definite basically. So because this expression depends on the local coordinate or the choices of the local trivialization of the vector bundle, so that it must satisfy the transition property. So it should satisfy the following property. This means the following. It's just coming from the elementary linear algebra. So if we choose the different like the trivialization or the different like the coordinate, so that and we just look at the overlap between two open subset U1 and U2, or just two different like the like coordinate from one to the other, then we are able to like look at the transition. So if we look at a sub 1 to a sub k as just the basis of the like the local like the description of the fiber wise like the basis, then we have the relation from one to the other for this like the basis, and there should be a transition matrix, and the transition matrix should be used to represent the matrix representation of the metric H in the following way. So if we use the matrix representation of the H with respect to this E sub 1 tilde to E sub k tilde, then let's just denote it by H tilde. And if we want to compare with the H with respect to the basis from E sub 1 to E sub k, then we have the following relation from the linear algebra. Just the effect of the coordinate, like the change and just coordinate change in matrix, yields the matrix representation of the inner product in this way, just so we notice from the basic linear algebra. So in particular, when we apply this for the k rank equals 1, so this means that the E, i.e., so this E is usually denoted by L, a line bundle. In that case, then the p bar to the t times p just becomes just a function or the scalar, so that this h, so in one local coordinate, it should be just simply denoted as just a h sub alpha. This is just a smooth function which is just positive, and we are able to compare two local coordinates, say h sub alpha, for the matrix representation, or just a scalar because it's just a rank 1, and we should just compare to just a trivialization, then this effect will be just changed as just a norm square, so that we can simply just denote it as just a norm square, and this f sub beta alpha just represent it just denotes the transition function. So that we have this following very simple relation. So in order to talk about the line bundle, then because the vector bundle depends on only depends on the structure of the local trivialization, and when we talk about the line bundle, so the data of the line bundle depends on the trivialization open set u sub alpha, and the way to change, I mean the transition function, that this governs the the R structure of the line bundle. And when we talk about the holomorphic line bundle, then we require not just a transition map as a just smooth map, but we require this to be non-vanishing. Non-vanishing condition should be required for the Hermitian metric, and this should be the non-vanishing holomorphic function defined on use of alpha intersection with use of beta. So that the data of the holomorphic line bundle, it should be just completely determined from the pair of the use of alpha with f sub alpha beta. So one of the important example of the holomorphic line bundle is when M is complex manifold. Then we already look at most of the time the canonical line bundle. So this is a notation for the canonical line bundle. That is defined the following way. So this, let's just denote M sub n as a complex manifold of dimension n. Then this K sub m is defined. And let me just skip to define the holomorphic tangent bundle, just to follow from the previous note of this complex geometry informal seminar. So that this is just a holomorphic cotangent bundle. But let me just denote in this way to just avoid any the confusion. So we have the dual of the holomorphic tangent bundle and take the n times wedge product, n times wedge product. So then we already have this structure. So in this the vector bundle, we know that the rank of K sub m is clearly equals to 1, of course, over C. So, and then we have the local section, and especially because we start from the complex manifold, especially this is a smooth manifold, so we can talk about the still local smooth sections. So what this means is that, so because we already take the n times wedge product on the holomorphic cotangent bundle, so the basis, one of the natural basis should be just this guy, and other types of basis just nothing but up to the scaling of the dg1 wedge to the dgn wedge. So the only difference fiber-wisely is just multiply by some function f, and for the smooth just a section, we just require this f to be just a smooth function over some local open subset. So that we have such a description of the local smooth the sections. Then if we just apply the transition in this perspective, then we from here we know how to describe this the abstract the concept of the transition with the matrix representation of the Hermitian metric defined in the line bundle. Then what do we know? So if we choose a different the open subset, say it is denoted by the indices alpha and beta, then one with one open subset, we have, for example, dg sub alpha. Alpha just represent the one choice of the open subset. So let's just use the upper index for the the coordinate component, which up to the dg and dg to the n with the sub alpha, then we should be able to compare in the overlap dg to the 1 sub beta, which to the dg to the n sub the beta like that. Then what do we know? So we know the effect of the so-called change of the coordinate, so that it should be written just nothing but the determinant of the matrix given by the Jacobian matrix of this the transition, so that the numerator should be with respect to the alpha, and the denominator should be with respect to the beta. And this ij runs from 1 to n, so n by n matrix, and take the determinant. This expression should be desired coordinate the transition function effect on this line bundle, so that now we know what f sub beta alpha for the canonical line bundle. Then the natural question then what should be the line the Hermitian metric, one of the natural Hermitian metric. Eventually the concept mostly we care only depends on the topological structure, but let's just define one of the natural the Hermitian metric based on this transition function. Then what do we know? Let's just assume we already have the Kähler metric, for example. So assume M is equipped. So for simplicity, let's just assume we already have the Kähler metric. was a Kähler metric that we already defined. And let me just denote Kähler metric by G as just a special Riemannian metric, so that with one choice of the open subset with the indices, let's say G sub ij bar, just mean that, so let's just use the inner product notation, so that ddzi alpha with ddj alpha. So we know this is a matrix, like the component expression of the Kähler metric. Then we know that we need to look at the also the effect of the changing the coordinate or changing the local open subset. Then that means that, so for example, if we look at Gij bar defined in the previous line, then if we choose a different, like the open subset, say ddz k beta with ddz l beta. So if you look at the effect of this guy, then we just need to change the coordinate accordingly. So for the k, in order to change this to be, for say index by I, then we should just put the coordinate change like the matrix given by dz to the k sub beta divided by dg sub to the alpha sub to the I sub alpha, so that we just change, and k are, there are two indices for k, so we take the summations, and we already changed the index from k to I by just putting this like the term. And for the this guy, we can just play the same game, and because this is a second like the component, so that we just need to put not just the dz beta l, but we just put the complex conjugate divided by the effect of the j's index, so that we get dg j alpha with the complex conjugate. Then this is the way to convert from the local coordinate with respect to index alpha to the respective index like the beta, from beta to alpha. So from here, what we know is that these are the description of the conversion in terms of the Kähler metric. Then what we can do, we can take the determinant with respect to the choices of the alpha open subset, and with respect to the effect of the open subset of the index beta. Then what we see is that there are now two such like the Jacobian matrix. So if you take the determinant, then it should be written as f sub beta alpha. We change the open subset from with respect to index beta to the index alpha. Then because of the two terms here, so that we should put norm square. So this must be the expression of the conversion. And by the way, so this should be taken the negative like the 2 for the power, negative 2 for the power, so that if we just make the form as this guy, then we just need to flip the numerator with denominator, so that it becomes 1 over determinant of g sub alpha equals f sub beta alpha norm square times 1 over determinant of g beta. So this says the following. So then we have the one of the desired Hermitian metrics, say h sub alpha, which must be 1 over determinant of g sub alpha, must be equal to f sub beta alpha norm square times h sub beta. We should get this. So this means, i.e., on the canonical line bundle, the Hermitian metric we should get can be written as a simply nothing but 1 over determinant of g, and other Hermitian metrics just nothing but the scale, like the multiple of just this guy. Of course, when the line bundle is just a canonical line bundle. So we have a one natural choice as long as we have already the Kähler metric. So this is frequently used. For example, if we simply just choose this M to be complex manifold, the complex projective space, and the Kähler metric or the fundamental form as the Fubini study just a form. So I divided by 2 times dd bar of log 1 plus c norm square with the choice of the one homogeneous open subset. Then if we just calculate this the partial d bar, then with respect to the one of the homogeneous open inhomogeneous open subset, so then if you just make the natural just indices, say ij bar, then one can simply just calculate with the effect of the log and the further derivatives. Then this would be 1 over 1 plus c norm square times delta ij bar minus g bar I times gj divided by 1 plus c norm squared. So this is the expression of the each like the metric component with respect to index ij. Then we can figure it out the each signature of this like the matrix expression would be written as, so there are n minus 1 numbers of 1 over 1 plus c norm square, and there are 1 of 1 over 1 plus c norm square to the square. So that from this like the matrix, one can just figure out the information of the signature, and therefore the determinant that determines the Hermitian metric on the canonical line bundle would be 1 over 1 plus c norm square to the power of the n plus 1 in denominator. One will get this. Then on the canonical line bundle, Pn. So the Hermitian metric can be chosen as we already discussed, 1 over determinant of G. This is just nothing but 1 plus c norm square to the power of the n plus 1. We'll get this. So, and this is the one example that we can just naturally just link from the one of the canonical metric, including the Fubini string metric, to the Hermitian metric on the one of the canonical, one of the important line bundle, and then we can just link from the differential geometric data to the quite either the algebraic geometry or some symplectic like the data. All right. So now we are ready to talk about the Chern connection. So the setting and the notation. So we already have complex manifold. We already have the one complex manifold, and we will have the holomorphic, like the vector bundle. So this E itself is a holomorphic like the complex manifold, and this pi via the local trivialization, so everything can be like chosen in the by holomorphic way. Just we require a stronger condition that rather than the smooth like the vector bundle. So there's a holomorphic vector bundle. That's the assumption. And one of the example, if you want to look at, is E can be chosen as a holomorphic tangent bundle. E can be chosen as a dual of it, and E can be chosen as a canonical line bundle, for example, and so on. So now what we like to do is, so for the complexified cotangent, complexified like the section I want to say. So let me just denote complexified dual of the tangent bundle or the cotangent like the bundle. If I just use just a section notation, let me just denote the section in this way, so this like the can be written as a decomposition, as we already discussed from the previous length seminar, this way, and this one I should take also the dual of it. So we already have this guy. So if we just denote S of alpha, for example, S is just nothing but the local smooth section without just talking, so we don't require this holomorphic yet. Eventually we use S of alpha for the holomorphic section, but for a moment just a local just smooth section of this E. Then for example, if we have a to the 1 of ME, so this is this consists of the section as a tensor product with the omega tensor by S of alpha. And if we denote a to the k ME, this is defined as a complexified holomorphic cotangent like the bundle with the k tensor for the section with the just a smooth section gamma on this holomorphic vector bundle. That's the meaning. Then what we can do is, as we are able to split the complexified, either the holomorphic or the complexified holomorphic tangent bundle or the holomorphic cotangent bundle, we are able to split into 1, 0, and 0, 1 part. We are able to do it for A1 here. So for A1, this guy can be written as A10 direct sum of A01. We get this. So if we have just a connection now, so let's just look at a connection. So let's just common notation by just del. So then we know that we just equip with the free slope for the vector, like the just a vector field, so that if we start from just a to the 0, so it's just we start from just sections on the vector bundle, then we just make it to be just a freedom for the vector, like the vector field, so that it just becomes a to the 1. So we have a connection on the vector bundle. This is just a guarantee without considering the complex structure or the holomorphic structure, but we know that we are able to split this codomain into 2 pieces. And we'd like to just look at this splitting. We have this. Then what we want to do is, because we have just a projection to a to the 1 to the a to the 1 0 and a to the 0 1, so that means that we are able to split the connection into 2 pieces via this decomposition. So let's just use the notation from the group status textbook. So a prime, nabla prime plus nabla double prime for the given connection. So this nabla prime just means the one of the connection from the same domain that maps to just A10 via this projection map, and same for the nabla double prime. So that we start from the a to the naught of ME. So start from these sections, it's the collection of these sections to the a to the 0 1. We have this. So now what we wanna do is, now we have a definition. Not yet. Up to here, this setting. So including all this like the setting. So now we have a definition of the Chern connection. So we'll say nabla is the Chern connection. Chern connection if it satisfies 2 conditions. It is a first metric connection. And second, so the projection to the 0 1 part coincide with the nothing but the partial d bar. If we just require this condition, so this means in fact the following. So i.e., so let me first just write as just a abstract for any holomorphic section S of alpha of the given holomorphic vector bundle, then we know that the partial d bar of S of alpha, because this is a holomorphic section, so via the local trivialization, this just being a holomorphic function, so at least compute wisely. So if you take the partial d bar, then this should be just a 0. We know this is already guaranteed. This means the following. So this is a definition proposition. So claim is that what we know is that take local holomorphic sections, say S of 1 to S of n. So via some trivialization, local trivialization from the complex like the Haussmann manifold, then what we can do is we can just put the connection here for each like the local sections. Then via that like the decomposition, we know that we are able to just split this connection to nabla prime plus nabla double prime. Then by the linearity, this must be equal to nabla prime S of R plus nabla double prime S of R. Then from the second requirement of the Chern connection, this must be same as a partial d bar s sub alpha, then from this is a holomorphic condition, this must be 0, then we only get this guy equals nabla prime s sub r. Then still we have a very slow for the vector field on this like the index here, so that we just denote this guy as a connection worm form from differential geometry. So that let's just denote this guy by theta to the alpha with like the gamma of s of alpha like this. So this is a connection one form. Then by this consideration, we already know that each like the components of the theta to the alpha with under like the gamma, this is from the construction, this must be 1-0 forms, 1-0 differential forms. There's no 0-1 part because we already kill everything. Then because we already keep, so by the way, I just want to make sure that we already have holomorphic vector bundle. And this H is a Hermitian metric, because in order to talk about the connection, then the metric should be required. So we have already Hermitian metric defined on E. So this is already like the given to describe this like the such a like the connection. So on this like the Hermitian metric H, so let's just plug in two local sections with the just arbitrary indices. So it's S sub gamma with S sub beta. Let's just put it so that this is some becomes some smooth function already, so that we are able to put the exterior derivative. We already can do this. Then we at least what we know is that this exterior derivative in the function level should be decomposed as a partial d plus partial d bar, so that we know we are able to write as a partial d h sub gamma beta bar plus partial d bar h sub gamma beta bar. So this is just a clear in the consideration of the smooth function. Then we know this is metric connection from the requirement of the Chern connection. So, and this is just a plug in the vector field for the arbitrary vector field. So this must be equal to the h of nabla s sub gamma with s sub beta plus h with s sub gamma with nabla of s sub beta. We should get this. So if we just plug in the vector like the field on this like the nabla, then we just get just a condition of the metric compatibility. This is just one of the equivalent just a description. Okay, then we know that this guy should be written in terms of the connection one form of the theta to the alpha under gamma, so that we should just write equals h of theta with alpha gamma of s alpha with s beta plus h with s gamma with theta delta beta s delta. We should get this. Then from the condition of the Hermitian metric, the first like the expression, this is come just from the linearity. We should take it just out without changing anything, so it just becomes just the same. H theta of the alpha gamma, and we just get h of alpha beta bar. We should get this plus theta bar of delta beta times h of gamma delta bar. So this must be guaranteed for arbitrary indices, so that from the type comparison, now we can convince that partial d with h sub gamma beta bar must be equals h theta alpha gamma h alpha beta bar, and also partial d bar of h sub gamma beta bar equals theta bar of delta beta h of gamma delta bar. We should get this. So this means without using the local coordinate description, the coordinate like the connection one from theta should be uniquely determined by the form of the partial d h multiplied by h inverse. Then this determines the existence of uniqueness immediately. So that this is a definition, let me say definition proposition. And of course, we already also said in the one of the previous seminar that if we require the given metric on M is scalar, then this. So for the holomorphic tangent bundle, so the unique such like the Chern connection equals to the Leibniz-Civita connection. So that, and from the consideration of this part, because this is already 1-0 form, and we know that the square is always identity, always just a 0, then this just requires that partial d or partial dd bar or dd bar plus d bar d are all equal to 0. So that if we just act by an additional partial d, then it must be 0. So from this one, so we can see one of the consequence. So we have basically Cartan structural equation from the general smooth vector bundle. So that says that if we have a connection one form, then if we just take the exterior derivative on this connection one form, this becomes differential two form. And if we take the wedge of this connection one forms to make the another differential two form, then they are actually the same. And this actually defines globally. This is what we already know. This is just a consequence in general. But if this E with the Hermitian metric, this M is a holomorphic vector bundle, then what do we already know? This partial d of theta is already 0 because this guy is already 0-1 form. So therefore, hence we have the modified Cartan structure equation. That is partial d theta minus theta wedge theta should be 0 globally. So this actually says that we are now able to describe the curvature as a global two form. So that we define capital theta with the index alpha beta as just we start from the local description of the connection one form. But if we just act by the partial d bar, so this idea was first came up with the mathematician Chern, Chern. Then this actually defines global one as just a 1-1 form, global 1-1 form. Then we have a connection two form. It's just a collection of all those like the components. So this K is the rank of the given holomorphic vector bundle. Then from here, then let us just say note. So this is curvature two form. So we already know what would be the local description of the connection one form. So theta to the beta sub alpha equals, if the Hermitian metric H is already chosen, then it should be H to the beta gamma multiplied by partial d H of alpha gamma bar. So this is we already know. Of course here H sub alpha beta bar equals, we just choose one local holomorphic sections and we just plug in H sub alpha and H sub beta. So then we just put partial d bar on this theta beta alpha. Then because we already know the description of the theta beta alpha, so this must be the same as, so H of beta gamma bar, and it becomes just a partial d bar, partial d H of alpha gamma bar. And then we, from the Leibniz rule, we also take the derivative on the inverse, and from the identity of the inverse of the matrix, so we should get H to the alpha delta bar times H to the beta gamma bar times partial d h sub alpha gamma bar, which partial d h of rho delta delta bar. So we should get this description, and we'd like just want to change this to for the just convention. We know partial d bar plus partial d bar equals 0. So if we believe it, we just take the negative sign. So it becomes, and let's just change the index here. So we will get, so just change as h to the beta gamma car, and let me just change here for a moment, and then say some consequence, and just copy. All right, we get this. So from here, especially we wanna define definition first Chern class. It is just nothing but just a trace define C1 of the global curvature 2 form is just nothing but the trace of the each like the components. So it's just nothing but the theta of alpha. Of course, it just takes the summation from alpha 1 to k, basically. So by using this form, so that if we just apply this to the previous like the expression here, so if you look at the first Chern class of big theta, then all we just need to do is just change, just make the indices of alpha beta as just the same, just that's all, so that we will get h to the alpha gamma bar with the negative sign, with partial d bar of h sub alpha gamma bar, we first get this, plus h to the alpha delta bar times h to the, let me also make the indices just as the same, alpha gamma bar times partial d h sub alpha gamma bar, which partial d h rho delta bar. So we get the description of the first Chern class, and one can see that in fact this description equals to the minus dd bar of log of determinant of h alpha beta bar. So now we get this. So and this is defined already globally, as capital theta is defined globally, so that we can, and we already know that, so exterior derivative is split as a d partial d plus partial d bar. We already know this is the case. So therefore, if we just additionally act by exterior derivative on dd bar, this must be 0. So that means that we already have the first Chern class as a closed differential 2 form. So therefore, we can talk about the drum cohomology class. Sorry. So yeah, this is still the definition. So yeah, this is not. So let me just change the notation here just a bit, because to just avoid some like the confusion. So let me just use as a sigma sub 1 here, so that the sigma sub 1 here. So this is just a differential 2 form, closed differential 2 form, so that we can just choose the representative in the class of the h sub h to 2 of the drum cohomology class. So actually this is the integral cohomology class if M is compact, but for the generosity of the arbitrary complex manifold, let's just take the complex coefficient. And this is the definition of so-called the C1 of E. C1 of O, without specifying the Hermitian metric H. So this concept in fact does not depend on the Hermitian metric. And from here, we are able to describe the curvature accordingly. So I think this note should be up to here, so that we have the definition of the Chern connection, and from the Chern connection, then we are able to describe the curvature to form, and from there we are able to describe the first Chern class. I think this might be enough. I'm just thinking whether or not I should just cover just a few. So let me just cover just a few more. So definition. So if we already have, I'm just thinking just a bit. So Hermitian metric on the holomorphic vector bundle on the complex manifold with the via the map pi, then we define. So U and V is the section from holomorphic tangent bundle. Then because now we have a concept of the globally defined curvature to form, so that we define the curvature tensor depends on this H. So we plug in U and V and act by the local holomorphic section. This is defined as just on the curvature to form. We just plug in U and V, and we just act by as a beta. And if we write this way, then this is a fact. Then we are able to actually recognize that this curvature 3-1 tensor can be realized as a canonical form in the Riemannian geometry. Like this. So that we can do differential geometry by using the so let me just put the metric just over here. So because we are just looking at the no, never mind. So let me just put this over here. Yeah, so we will get this, but I think I can just stop here before going further, because it could be too lengthy if I just try to go further. Yeah, so this the note is to cover the Chern connection and the curvature to form and the first Chern class, and that's it for this note. And thanks for watching this the video. So I will initiate the further conversation in the informal messenger based on this the note. Yeah, thanks for watching. Goodbye.